Podemos começar? Tá, beleza. So, hello again everyone. So, I have another announcement. So tomorrow we will have class also, but I will not give this class. It will be João. He will give the class tomorrow. So let's go back to the construction of the long-range contours. So we had the definition of MA partition of a finite subset of ZD. And we asked this MA partition to satisfy two things. So it is a collection of subsets, finite subsets, such that it satisfies two conditions. We have the condition A, where we ask that gamma is a partition of A, and more than that, we need the following. We need the following property to be satisfied. So for any gamma I, gamma j distinct elements of the family, so there exists a unique connected component of the complement of J such that gamma I is inside C. And then there is another condition, the most important one, the condition on separation, okay? And this says the following, that for any distinct elements inside gamma A, then we have that the distance between these two is larger than m times the minimum of the volumes the power A over D plus 1. And remember, M and A are positive real numbers. So, for instance, in applications, we will choose M later when we are proving the bounds on the energy. And for A, the A can be chosen as 3D plus 1, the minimum, alpha minus D, and 1. So as you can see, A becomes larger when alpha is closer to D. So what we did yesterday is that we were proving that the following proposition. So for any given A in ZD finite subset, there is a possibly non-trivial MA partition. So what we did during the proof was that we introduced something that we called M cubes And these m cubes are defined by cmx, where x is some point on ZD. And what we do is that we take the interval 2 to the power m xi until 2 to the power m xi plus. This is an interval. Then we only look at the integer points, and then we take the product for each one of the coordinates. So what this is doing again is the following. So if you have z2, for instance z2, and then you take x equals to 0, what would be c0 1, for instance, would be something like this. So would be something like this cube, and then for this is c1 0, okay, and then we can take actually wait, so this is choose actually it's not this, it's this smaller one, so it's 2 times 0, so 2 times 0, just one, let me see one thing. Yeah, so exactly, so is exactly this one, because this go from 0 to 2, 0 to 2, because m is equals to 1, and this is open, so actually, okay, actually we get this. And then the other neighbor is this cube right here. This is the cube right here. And then if I can keep translating x, then I will get something like this. And as you can see, if I keep translating the cube, then I will cover all ZD. And the advantage of this construction is that when I grow the scale, when I take m equals to 2, for instance, for x equals to 0, then I will get this cube to be the cube in the next scale. So this is C2 0. So what happens is that we can change, by changing m, we get larger and larger cubes. And with this larger cubes, we still can cover the ZD with disjoint cubes. And the advantage is that the last step decomposes exactly the cubes in the next step. So we will use them to construct, we used them to construct the MA partition. So what we did is that we chose scales, we chose scales dependent on some positive integer, okay, r, and these scales were chosen as we only work with CRL cubes, so RL cubes for L larger than 1. And okay, and for each one of these scales, these cubes, we defined graphs. So we have graphs. So for any finite subset of ZD and a given scale, RL. Okay, so we can take the minimal cover of A by RL cubes. Okay, call it this minimal cover V. Okay, so it'd be VA RL. So this is the minimal cover, and this will be the vertex set of the graph. This will be the vertex set of a graph. Of a graph where the edges are given by the pair of cubes such that their distance is less than m2 to the power a RL. Okay, so we have this, and then we define it a procedure to analyze this in different scales. So what we did was we start at L equals to 1, then you define GR of A, this graph, then you take the connected components so take the connected components of the graph in the first scale, so G R A, this graph, remember, so it's a pair with these edges and these things, and then you take the connected components G, okay, and then you define it you define AG as being the set A intersected with all the cubes CRL that is contained on the vertex set of the connected component G. Okay. So again, just to see a picture. For instance, if this is your set, and then in the first step you have something like this, a cover by cubes. Take a cover by cubes, okay, and suppose that these distances are very large, so these distances must be larger than M2A, so this is large to AR, R, okay, so what happens is that if these distances are large, so there is no edge. Since we made this rule, there is only an edge if the cubes are close. So this means that the graph formed with the cubes from this cover over here, it will have three connected components: G1, G2, and G3, okay? And then what this set is doing is that given a connected component, G1 for instance, then you intersect the part of A that is covered by the cubes in the vertex set of G1. So this will be AG1. Okay? So once you have this, then you define, once you have this, you define the set, P1 as being all the AGs where G is a connected component, GR, and the volume of AG is less than 2R D plus 1. 2R D plus 1. It's less than. Okay. And then you define an A2 as being the set A minus the union of AG in P1. So this, what you are doing is that you are reducing the set A. So then you can continue the procedure, but now with in a larger scale. In larger scale, what I mean is that I just changed this L. So we started with L equals to 1, and then we go to L equals to 2. So so you can define, you can make inductively. So since we did this yesterday, we're just giving a quick reminder. So inductively, we define the A in the next step as being the A of the step that you are minus the union of the components AGN, where AGN is inside PN, and PN is just the A and G's, where G is inside GRN connected with the volume of AG less than 2RN D plus 1. So what is happening is that when you go to the next scale, you also change the condition that you put for extracting some subset AG. So, and this condition is given by the volume must be larger. So, and since the cubes are invading the lattice and their volume is going to infinity, so eventually you will cover all of the remaining set, and also this quantity will certainly be satisfied because the set AN is decreasing in size, and the volume, this condition in volume is increasing because it's 2Rn, so eventually this will always be satisfied, and then eventually AN plus 1 will be empty, so the procedure stops. Okay, and then what we did was to show that that it satisfies condition. What it showed is that for any, okay, so what is the MA partition? Of course, following this procedure, the MA partition is just the union. So gamma A is just the union of Pn from n starting to 1 to some n, where n is the smallest integer, where an is the empty set. So the first time that you hit the empty set, so you have everything, so you don't need to continue the procedure, okay? And then the main partition is this one. So, and yesterday we checked the B condition. So we actually checked that for any two members, gamma I, gamma J, inside gamma A, given by this definition right here, we checked that the distance of gamma I, gamma J is larger than m times the minimum v gamma 1 v gamma J power a over d plus 1. So we must show that it satisfies the condition A now. So that it is indeed a partition, it is easy to see, okay? But we need to check the condition, the second condition, and this the second condition is related to the fact that given gamma I, gamma J distinct inside that collection that we defined, then there will exist a unique C connected component of the complement with such that gamma I is inside this set. So the proof is straightforward. So what you do is that you suppose that this doesn't happen. So suppose that gamma I intersects, okay? So it intersects two different. So suppose that there exists C1, C2 connected components of gamma I, gamma J, the complement of gamma J, that gamma I has a non-empty intersection with both of them. A non-empty intersection with both of them. So what happens now is the following. So since by construction, we know that there is a scale, there exists a scale RL for some L larger than 1 and a connected component. And a connected graph, okay, a connected graph, such that gamma I is actually equals to A, this scale, AL, okay, intersected with G, okay? So what happens now? If we take, okay, since both of these conditions happen, this means that there will exist cubes C actually RL cubes let's say CRL and CRL prime that are in the vertex set are in the vertex set of G that intersect one of those connected components. So let's say CRL intersects C1 and CRL intersects C2. Okay, so the distance between those two cubes, what is the distance between these two cubes? So what is the distance between these two cubes? So take a minimal path in ZD such that the size of its path, this path, is exactly the distance of these two cubes. CRL, C1, CRL, CRL prime. Okay? So since these two cubes, since they both intersect the different connected regions, this means that this path must pass through gamma 2. Oh, sorry, I said gamma j. So it must pass through gamma j. So let me make some drawings. So if you have, let's say, something like this, we already saw this figure right here. So, and you have a cube that is inside here, and a cube that is inside here. Okay? So what happens that the minimal path connecting both of these sets right here, so since they are living in different connected components of the complement, this must pass inside gamma j. But remember, gamma j was at some point. Okay. So I must make another assumption here. So So without loss of generality, I can assume that that gamma 2 was not retirada, was not sorry, removed. Yeah, was not removed in the step L. Okay, was not removed in the step L. Because okay, if it was, then you change both of them, and then I am in the situation again. So what this means is that since this component was not removed in this step, this means that there was a cover here of this set. There was a cover here of this set, and this was from a different connected component that generated gamma 1, gamma I actually. So since this was from a different connected component, this means that the distance between these two cubes must be larger than M2ARL. Okay? Because since this cube is not connected to the graph covering, to the part of the graph covering gamma 2, so there is no edge between them, and by our construction, there is no edge exactly when the distance is something like this. Okay. And why this finishes the proof of the result is that again, since CRL has a non-empty intersection with C1, this connected component, and I have a non-empty intersection with this one, and these two cubes make part of another connected component of the set. This means that they cannot, since they intersected this set over here, they cannot intersect gamma 2, because otherwise it would be connected to gamma 2. So actually, what these conditions give us is that CRL is contained in C1, and this is contained in CRL. Oh, sorry, this is contained. So CRL prime is contained in C2. Okay. But this works for any pair of cubes that you take from G. If you have any pair of cubes of G that one lives in one connected component and the other one lives in another connected component, then you get that their distance is larger than this. So since this holds for any pair of cubes, this means that I created two components of the vertex set that are not connected. So, but this is absurd because I assumed that G was connected. So G is connected. So this means that my assumption that gamma I was intersecting two different connected components of the complement is false. So this construction satisfies condition A. Okay, and of course we must. I showed that this construction works. and we actually use them we use it on the counting arguments, but it's not the one that we will strictly use in the construction of the contour. We will actually take the finest one. So for the contours, we will take the finest one. And what this okay, so what this means is the following. So if I have the set, let's say, of all MA partitions of a given subset A, then I will take the one that is finest in the sense of inclusion of the subset. So for this to be well defined, I need to prove another thing. I need to prove an important property that for any, so if gamma A and gamma 2 and gamma prime are MA partitions, of A, then I can create a finer one. So, okay, in what sense? In what I can create another one, let's say gamma prime, that satisfies the following, that any it's finer in this sense. So, what I mean by finer? So, gamma 2 prime, gamma double prime is finer than gamma A if any element here, gamma 2 prime inside gamma 2 prime, is inside or better is contained in some gamma from gamma A. This is the sense that I'm using as finer. Okay? So what we need to do is to show is the following. So if I can show that given any two MA partitions, I can create a finer one, then I can define the finest one as the intersection of all MA partitions. Okay? So if this is true, so if the proposition is true, then I can take the intersection let's say the intersection of all of them, and this is the finest one. So what I wrote intersection this way, because the intersection is it will be in the sense that I will use to prove this proposition. So the proof is the following. So given gamma A and gamma prime A, then I can define gamma double prime A as being the collection of all gamma, so gamma prime, the intersections between elements, where gamma is inside, the first gamma is inside gamma A, the second gamma prime is inside gamma A prime, and the intersection is not, the intersection is not empty. So I just take the collection, I'm just refining this this partition with and collecting when they are not empty. So let us show condition B first. Let me show that condition B is satisfied. So okay, so if I take gamma 1, gamma 2 that are different inside gamma A, and gamma prime 1, gamma prime 2 inside gamma prime A, again distinct, and moreover such that this is not empty, and also gamma 2 is not empty. Then what I can say about the distance? So remember that the distance between two sets is just the minimum overall the distance of x and y. So this is just the minimum of the distance xy, where x is inside this set, gamma 1 prime, and y is inside gamma 1 gamma 2 prime here. This is just the minimum over this. So since I'm taking the minimum, if I enlarge the sets, the minimum can only decrease. So this will be larger than, for instance, the minimum of the distance x minus y from x 1, y inside gamma 2. We can choose something like this. And what is this? This is exactly the distance between gamma 1 and gamma 2. But since this satisfies condition B, then I know this is larger than m times the minimum of the volume of gamma 1, the volume of gamma 2, to some power, AD plus 1, okay? This is positive, okay? So, and another thing is that the volume is monotone with respect to the inclusion. So if one set is contained in the other, so the volume, so what I mean is that if lambda is contained in the lambda prime, then the volume of lambda is contained in the volume of lambda prime. So this means that this minimum is larger than m minimum of v gamma I, v gamma 1 intersection with v gamma prime, this volume, and then this volume here, the volume of the other one, the power AD plus 1. So okay, it satisfies condition B. So now I want to show I want to make an interesting comment that started with a comment by Kelvin that about the necessity of defining the condition A in the way that it is. So you can just, for instance, you could just ask that gamma A is something that is a partition of the set A and satisfies condition B. So this is okay. And what I will show now is that the intersection will also satisfy the condition A, but I want to draw attention to the fact that if only one of them satisfies condition A, then the intersection will satisfy the condition A. So for condition A, we do the following. So again, over with this hypothesis over here. So what we have is the following. So since gamma A satisfies condition A, then what happens is that there will exist a unique C connected component of gamma 2, the complement, such that gamma 1 is inside C. And again, C is inside gamma 2, the complement. But if it is inside this, it is inside in the union of gamma, the complement of gamma 2 with the complement of gamma 2 prime. And what is this? This is just gamma 2 intersected with gamma 2 prime, C. So this is the complement. The connected component inside the complement over here. And another thing over here is that this contains the intersection, of course. So we get that this satisfies the condition A. But notice we only use that gamma A satisfies condition A. So there is no need to the other one to satisfy condition A too. And since we proved that the construction from João also satisfies condition A, this means that the finest one must satisfy condition A. So this means that actually condition A can be dropped. Did you follow the? Did you follow? Okay. Gilberto. Okay, so what time is it now? Okay, now we proved that now we proved everything that we need for the construction. So of course there are many more things to say, because there is a reason why the condition A is here, and the reason is that we need to define to properly define labels of the interior. So we need to define if a contour is a plus contour, if it's a minus contour. So we use condition A in this definition, but I will not talk about this here. Actually, if you want to see how this more fine details are handled, with how you handle these finer details, so you can check many places. One of them is João Stevens, and also I guess one that will be important is João's talk next week at his PhD defense, where he will do this. So okay, what I want to do now. Actually, what I want to do now is to finish. I will stop here. Eu vou fazer a apresentação agora. Deu 1 hora de aula, tá?